Happy to welcome Jinchao Xu, the Vern Wilman Professor of Mathematics at Penn State. He'll be talking about training and analysis of numerical PDE by neural networks. Take it away.
Okay, thank you, Greg. Thanks for having me here. Thanks, the organizer, for having me here to give this talk. Today, I'm actually going to talk about some very simple questions here. So there's a lot of success, of course, deep neural network for things like image classification, natural language processing, and recently, of course, there's quite a growing interest in applying neural network for solving PDEs, and so the question I'm asking is that suppose you take any, let's say, I call it numerical realizable discretization method to solve a PDE based on neural network. How much can we actually prove about the convergence, like a convergence rate, like what I have here, without making any unverifiable assumptions? How much we can prove, do a rigorous proof. Another one I want to say that, how much accuracy can we actually numerically obtain without worrying about the mathematical rigor? I just say if I have an algorithm, I can implement it. And this problem has much to do with what Professor DeVos talk mentioned a lot about this, talking about this stable algorithm and all stuff like that. And so to me, the answer to these two questions actually has not been very encouraging, because when I look at the literature, and there's always there are many analyses, many papers, there's always come with some kind of assumptions. And when you see the numerical method, you see there's some kind of convergence of, especially when the number of neurons gets large, you stop somewhere. But when we're trying to repeat those tests, in my group, we can really see it. We cannot continue to get the asymptotics correctly. So I'm actually giving this talk here one way to probably because there's lots of papers in this topic. Frankly, I cannot keep up with them. And if anybody can help me to answer these questions, and you have, for example, you have an algorithm, you say you can observe the asymptotics and things like that, I'll be appreciate to know those results. So I would apologize that in advance if I miss a reference that this related to these two questions. Anyway, so I'm coming from a finite element background. I begin with a finite element method. So you talk about piecewise linear method. So this is a piecewise linear, and you usually have the basis function, we call a height function, like this. And this base function can be written as this locally supported basis function can be written as some scaling and translation of these fixed things. So by writing this basis function at the top can be written, some combination of ReLU, which is the most popularly commonly used activation function. And so we can say that the finite element method is in this neural network, what we call. And so I'm trying to relate to this finite element. So you can think about a neural network is, in this sense, is some kind of generalization of finite element by freeing those nodes, moving arbitrary nodes and a grid point. You can also do higher dimension, you simply replace this linear function in 1D by multi-dimension. You also get a piecewise kind of a linear function. And excuse me, may I ask the organizer to disable this security, let everybody in, because every time somebody want to come in, there's something show up on my screen. I'm sorry. Is that possible? You could go to security, you enable the waiting room on disable it. Then people come in not being asked. I would appreciate that because it shows up on my screen. I don't know why. Maybe I didn't set it up.
Okay, I think maybe it's disabled now.
Okay, I appreciate that. Thank you. It's kind of distracting me. I don't know why.
Sure.
And that's why I'll be doing the. Okay, and the thank you. I agree. So again, I'm going to choose my very special activation function to be the ReLU to the case power. So if you do that, and this multi-dimensional this neural network function is actually a finite element of a piecewise polynomial degree k, and so you can also do this deep neural network. I guess in this audience I don't have to repeat. So the interesting thing is that for the deep neural network, as a set of functions, the ReLU DNN with the deep network is actually the same as linear finite element, what we do for ages. And if you do the ReLU of the k, and it's piecewise polynomials of higher order, but but it's different. Only in the linear case are the same, but it's going to be piecewise polynomials with on some kind of very strange grid with maybe curved boundary or stuff like that. But anyway, there are piecewise polynomials. I'm interested in this kind of neural network functions. The approximation property, this again, one of the things which again I'm going to mention what Professor DeVore just said about the stability issue here, and I'm going to actually address this constantly, repeatedly in this talk. So in this particular case, the stability is imposed in this coefficient sigma AI. This L1 is bounded. This is what I call a stable neural network approximation. And if you do that, you can also do more general kind of a dictionary. And so you, given this M a priori, you just want to consider, what kind of approximation, what kind of function this what I call a stable neural network can approximate. And so you can think about this like a dictionary. You take the closure, if it's m equal to 1, that's called a B1D. And using this one, actually, I use the notation from Ron DeVore's this survey article, and they call it K1D. So you can treat this as the unit ball. So you can take the informal R such that if this R time in the like the radius R or F is in there, so you can call this the norm. And so then this will be the unit ball, and so then you define this K1D as this norm is bounded. This is what we call this is actually you can prove it's a Barak space. And so the interesting thing is that one of the questions I asked earlier, and because Ron mentioned quite a bit about the model class. So a natural question to ask is that for any function at all that can be approximated by my stable manifold, my stable neural network, what kind of function class that should be? So we identify here is that it is affine only if in this K1D space. So we're talking about the qualitative convergence in norm, the strong convergence, if it can be approximated by this this function class at all, and this function class 7, and this function to be approximated has to be in this K1D. So it's the minimal or largest function class that can do the job. So that's the qualitative convergence, but you can also have the quantitative convergence is that you can actually get this, this end of the negative half of things, which is shown in the literature everywhere. So, so if again, it is very important to have a stable neural network. But if you have the stable neural network, then we identify the functional class. It is actually this K1D space. And in the most of the existing literature, you get to the end of the negative half. And it turns out for the reload to the case power, we can get this estimate 15, pretty much the upper bound, the lower bound matches. And you can get the extra power here, minus half minus 2k plus 1 over 2d. So what this means that if you have a function that can be approximated at all by this stable neural network, it has to be in this K1D. But if it's in K1D, in the previous page, I said it has to be n to the negative half. What we actually say is that you get extra power, minus 2k plus 1 over 2d, but this number goes to 0 when d increases. But nevertheless, this is the optimal bound. We can prove it's also a lower bound, probably some kind of logarithm. And that's but if you compare this with the finite element method, and you would get a, if you compare these two, you actually get a better convergence. So now if you remove this this bound, sigma AI is bound. Now this is coming again about around what you call it, maybe this is not stable. If you don't have stable, then you have superconvergence here. You can actually, you do have the superconvergence end of the negative k plus 1. And if f is very sufficiently smooth, but again, this is what I call unstable approximation. So if you don't worry about stability, you can get a very high order of accuracy. And this is going to, if you compare with finite element method, and you can raise the power of d in comparing with the best of finite element approximation. That's really super convergence, especially for higher dimension. And but the price to pay is to remove the stability constraint. So we have a piecewise polynomials, and we want to use the numerical solve PDEs. So let's do some simple PDEs. Let's do this 2m's order. Maybe you can think of it as Laplacian. And the way to do is that even the higher dimension with high order, well, I'm talking about, sorry, I flashed it too fast here. You think about this PDE as like 2m's order PDE in any dimension. So I want to say I'm going to have to solve this by my numerical, my neural network. And so the interesting thing is that this, if you to the raised power, you can actually this thing is a subspace of HM. In the finite element, you get a conforming method or even spline to get a piecewise polynomial. It's globally smooth. It's highly non-trivial problems. But neural network is pretty trivial. Now the question is that so this piecewise polynomial in this shallow neural network is going to be piecewise polynomial in this very funny looking grid there. And then let's take a Riemann boundary problem. The way I solve this problem here, I'm going to just do minimize this Discrete interval. If you do if surprisingly, you can actually do you minimize the Discrete interval, so you minimize in the Discrete in the neural network spaces, and surprisingly, you can actually prove it's still best approximation, even though this is a highly nonlinear optimization problem. And you can still get the best approximation, which is not pretty simple to prove. But if you did the best approximation, if you use the superconvergence estimate, or you can use the stable estimate, you can get the error estimate. So, so that's the theoretical result we can prove for neural network. But I wouldn't call this a numerical realizable because you have other issues. You have, for example, numerical quadrature. So this is just only a theoretical issue. In practice, you have to worry about other things. But again, this has lots of superconvergence. If you compare with finite element method, this is without worry about the stability. But even when you put the stability into account, you can also get superconvergence, but not so dramatic. So I'm coming back to the, so if you look at this comparing with finite element, this is piecewise polynomials on curved elements. And you can get a very high order of accuracy. And you can even get a spectral accuracy when you increase the number of layers. And even k equal to 1, you can do spectral accuracy. And if k greater or equal to 2, you can reproduce a high order polynomial. I have some papers here I mentioned here for any arbitrary order. So I think this neural network function is kind of selfly adaptive. Both, I would say, you can, because it contains a piecewise linear function. For we have proved that it contains any arbitrary adaptive locally refined mesh. So you can do local adaptivity, but you can also some global adaptivity. So it's kind of multi-scale adaptivity in some sense. So I find this kind of class is very interesting. But again, the question that how do you actually solve the optimization problem? There's many issues I'm going to address right now. So for example, the how do you if you suppose you do the minimization of the Discrete integral, then you need to evaluate this integral. So we're gonna have to do it doing some of the numerical quadrature, okay, for 12. So you can do a different kind of numerical. There's actually quite many papers in the literature analyzing this with various different assumptions so I guess the two approach you can think about, you can do the random samplings and for this numerical quadrature. Then you can, again, maybe you can use the Gaussian quadrature. You can pick the. So in terms of the data, and you think of using machine learning language, and this integration point you can think about the training data. So then you want to say, okay, after the training data, if you do these things here, so how do you estimate the error? That actually what I would call the generalization in this context. So to do the convergence analysis with this numerical quadrature would be to do the generalization for this very simplistic problems of numerical PDE. So we're doing the generalization things. So if you go to the, I'm the finite element guy, when you go to the area analysis, if you do numerical quadrature, one of the things which is being used is what we call inverse inequality, this 28, or maybe Bernstein inequality. If you take the higher superlative order, something in there, it will be bounded by a certain power, polynomial power of this number of neurons. That's what we call Bernstein inequality for the low order subgroup spaces. And many attempts have been made in the existing literature by using this 28, making the assumption that Bernstein inequalities actually hold to do the analysis. But the bad news is that the Bernstein equality does not hold for this neural network, at least for the reduced case power. We can construct a counterexample. You cannot prove Bernstein equality for neural network space. And we've done in this paper. So this analysis, based on the assumption of the Bernstein equality, would not apply to reduced case power. It could apply to the other ones, but I'm talking about the reduced case one. So the comparison again is this to solve this issue again is the stability. You need the stable neural network. The stable neural network again is the coefficient will be bounded. So in this case, now if you solve this, so you instead of H1 omega, you actually we restrict the function class in this K1D space. You minimize that, and so when you do the numerical quadrature, you also minimize this this function class is K1D. So the norm is bounded by M. That's pretty much equivalent of saying that the coefficient is bounded L1. So we have worked out this analysis here. If you assume that this dictionary is bounded in the WK infinity norm, and if you do that one here, so because you choose, this has to do with the smoothness of the activation function. If they reduce the case power, if you scale the things appropriately, the 32 will be satisfied. So this means that this function class, my stable, this K1D space is pretty smooth, and it's very small functional class. And this is what called around called a model class. But we're not talking about a very big logic class. We're talking about something very quite smooth here. That's the only the theorem can work. And in this case, you can do the numerical quadrature. You can prove the numerical quadrature because the integral, the integrand, which even in the discrete case is smooth, you can do the numerical quadrature. You can use, for example, if you can do a Gaussian, you can do the estimate 33. And so now, so again, we have two types of we have two types of discretization. But if you do the random sampling, again, you think about the integration policy is pretty much analogous to the training data from the machine learning language. And one way to one of the important quantity in this, when we do the generalization is Raman complexity, and I assume most of people know this, the definition of it. It's showing in 34, and we have proved that for Monte Carlo method, and if you do the if you use our stable manifold, the stable dictionary or stable neural network, the 35 will be bounded. You can prove that this Raman complexity is bounded by n to the negative half. From there, you can say that on the 36 that we can prove that inside the stable neural network function, the K1D, this model class. So the Discrete interval, you have this n to the negative half, and in this case, you can actually, this is what I call the 37 is the generalization error, because you do in this case, if you do random sampling, it would be you do the expectation, and so now we can obtain the 37. So there's you have the sampling points, n is number of neurons, and if you balance that, you can. And now the question here, that, okay, we have proved the 37. Now the question here is that here's something I need to get some help from the audience. So suppose you want to say, I'm going to minimize this or the Discrete interval. Suppose the most popular method used is the SGD or the Adam method. The SGD Adam method use the machine learning, of course, almost exclusively. But most people in the literature use this method to train this numerical PDE things. My question is that can you train the numerical PDE to see some asymptotics? we have read as many papers we could read, and try to repeat what people report in the literature, and we just could not go. If you in the very beginning, if the number of neurons are not that many, you can work very hard at the other method. You see there's some topics, but if the n is large, we just cannot do it. We just couldn't do it. You get things get flat. This is what I call a numerical error, and we don't observe the asymptotics. So again, there's a lot of Ron mentioned earlier. There's a lot of parameter tune what works as. I asked many of my students collaborate to work on it. We just could not keep going. When n is getting large, you just, no matter how hard you work, you cannot do it. And so I called people I know. So how could you do it? And for example, I called, I think like some people. They actually told me that, wow, this is what they also observed that. It's what some people call the optimization error. It's kind of, you have some kind of, and again, I think this other method, or this method when you train these things, there are stability issues. I think this problem is really when you have this unstable method of this which Ron mentioned repeatedly in his talk, is that I believe this is quite relevant here. You just, when n is large, it becomes so yield conditioned. This reminds me when you solve using Gauss elimination for the Hilbert matrix. When n is large enough, you just cannot get good numbers. And so the one I'm going to show you here is that this is my second. The first one is this numerical PDE result I'm going to show you later on. If you do the other method, you afterwards just get flat. So we are using this thing called a greedy algorithm, which I'm going to show you in a moment. It's a different kind of training algorithm for this particular case. You do see the asymptotic. This is the point I'm trying to make here. This is what I call the greedy algorithm, which again is in Professor DeVos, and his group written many papers on this. There's something called an orthogonal greedy algorithm. And you solve what we call argmax problems. You pretty much if you take the data fitting here, you just look at the residual. You try to get the best direction in the residual direction, and you do the orthogonal projection. So you keep going. And sorry, I'm using two different notation here. In the numerical PDE case, the residual is the gradient of this Dirichlet interval. So it's kind of the gradient descent because you're looking for the gradient direction, and which is matches the direction as much as you can in the dictionary. So you go from there. And this 40 involves this orthogonal projection, but the 41 is called a relaxed greedy algorithm. So every time you do is either a neuron or something, and you just keep going. So we have started quite a bit of a neuron, with I should mention that all this work is done by my postdoc, Jonathan Siegel, and we have written many papers on it. Jonathan especially spent a lot of time trying to understand all this greedy algorithm. In the existing literature, maybe wrong, you can correct it if I'm wrong. I think most of if all the results, the greedy algorithm can only achieve n to the negative half. And we just studied, okay, maybe we can do better for this special dictionary. Now, it turns out, if you take this stable K1, this PK, this Reynolds case power, we can actually achieve the optimal rate, 42, by using orthogonal greedy algorithm. Well, very, very happy with this result. And a stable method can be trained. Unstable method, we don't know how to train it. Stable manifold. we can prove. I think I believe this is the first result that is bit to the n to the negative half. I'm not 100% sure, but we couldn't find it. So so again we in this the stable neural network, we approved the 42 is the best approximation, but we can also achieve this best approximation by this greedy algorithm. That's and also the thing, the analysis I mentioned before. If you do the numerical quadrature, you do sampling, you also have to be in the stable neural network. So I can do the analysis. I can also do the algorithm. So from there, you can actually show if you do the relaxed greedy algorithm, because this is kind of a convex combination. You can actually prove that during the training process, my U of n is always stay in this K1D space in the same bound. Then you can prove that this target function is bounded by 1 over n. But there's one open problem right now. When you do the orthogonal greedy algorithm, we have not been able to prove this one yet, because but numerically it works very well. Anyway. So you can so that, but there's a this what's the greedy algorithm? But there's a catch. You have to solve this what I call Argmax problem. You find this best possible direction in the dictionary. This involves d-dimensional optimization problems. Everybody, we all claim the neural network is going to be great for high-dimensional problem. I'm just asking a kind of naive, a simple question. And for let's even worry about the low-dimensional problem. For the low-dimensional problem, this is a feasible thing to do, but you can maybe do brute force. That's what we did in the numerics. But the larger D becomes a high-dimensional problem. Then you have to also worry about these things. There's some books, I think, working, various literature people talking about these things, but we haven't. But the way we do is that we just brute force resolve for 1 and 2 and 3D. That's is doable. By the way, with this greedy algorithm, we can achieve this bound, asymptotic bound numerically. But we do not know any other method, SGD other method. We could not get them to work to get a asymptotic rate. We just couldn't get it. Again, if anybody in the audience, you know, I'm sure that many people know better how to tune this other method. And so we can talk about the numerical experiment here. Sorry. So, for example, I'm going to again, I think Ron mentioned his talk about you fit the x square, you do the SGD. It's very difficult to fit the x square to use SGD or other method, but it is pretty easy to fit by this orthogonal greedy algorithm. You can actually see that we actually proved, of course, in this stable, neural network and stable function, then you can actually have achieve the best approximation. We actually numerically realize that you can see the asymptotics. Increase the number. If you increase the number of neurons, you see the asymptotics, but you cannot see that in the. For example, I can take this one-dimensional problem here. And again, you can use the orthogonal greedy algorithm. You can achieve the asymptotics by provided by our theorem. But now, suppose you want to solve this by either method. Again, if you solve this by either method, in the beginning, this either method looks very good from like n to the 248 neurons. Actually, get a pretty good accuracy. But if we increase the number of neurons, you iterate hundreds of thousands of iterations, you adjust the learning rate, all that. And we just couldn't get it. You get flat. This error will get flat. But well, the greedy algorithm, you get the asymptotic rate. You get all the way to 512, you can keep going, you get that. But not by either method. I'm not talking about theory here. We have a theorem for the greedy algorithm, but I'm not talking about the theorem for, but I'm talking about just practically you tune your method to see the new, suppose maybe use your computational power, computing power. If you use a bigger computer, you do a larger n. Can you observe the numerics? But when n is getting large, we just couldn't do it. But again, maybe somebody in the audience know how to do this. And you can actually, I mentioned this bit earlier that the neural network kind of has the self-adaptivity. You can do a local adaptivity, global. It's all in this optimization algorithm. You can just, there's an underlying grid in 1D, but if we tested some kind of singularity, it gets it right, actually. And you can do force order problem. You can also use the greedy algorithm. You get a pretty good asymptotics. But again, if you do the other method, there's no way we could do it. After a while, we just couldn't get anywhere. You can do 2Ds also. And so in this, we can, we have the theory for the linear problem, but we can prove, but the nonlinear problem, we don't have a theory, but we run the nonlinear problem, we still get the predicted accuracy. Oh no, the accuracy like in the linear problems. And so we use we also tried some other nonlinear problems, Poisson Boltzmann and all that. You still get good at you see the asymptotics numerically. But again, we're still doing the theory. So so I want to summarize the things that I like this deep ReLU K because neural network, because the piecewise polynomial of the degree of piecewise polynomial of continuous function, so very closely related to finite element methods. And so you want to do a comparison of so you told now the question that this kind of functional class, what kind of functional class or maybe model class this kind of neural network can be approximated. If you impose the stability in this neural network spaces, so the function class is this K1D is this what in the statistical literature is called a variation space, and in deep neural network, some people like Weyla, Professor E would call a Barron space, and we can call a Barron space in general, and it is the largest space that is for stable approximation in the sense that the coefficients L1 is bounded. It's the largest. That's the if and only if things. For the ReLU to the case power, we can get the in this functional class, we can get this optimal error estimates. This optimal is because you get an upper bound, you also get a lower bound. And the third one, I'm just thinking which were very high is you can now it becomes when you have a stable neural network, you can actually train it, you can actually get it in terms of by this orthogonal greedy algorithm, we can get the same rate. But if you so this of course it amounts to solve a optimization problem of D dimension. If D is larger, that I mentioned there's an issue there. But but if you remove the stability, you can get a superconvergence. And again, so when you do the analysis for the neural network for the solving the PDE, and we emphasize that the Bernstein inequality doesn't work. We have counter example, so you cannot use traditional methods to analyze it. But Bernstein inequality is satisfied if you do the okay, I'm saying the Bernstein inequality does not work for the neural network space. It's for the unstable one. If you do the stable one, it's okay. Actually, I'll be more specific. If you do this work in the stable neural network, you can do the convergence analysis, very rigorous. And then again, use the greedy algorithm to solve the discrete energy minimization. You can numerically observe, we can also theoretically prove. And, but we are not able to do this for other method numerically. And now we're all kind of excited these days, many of you using neural network for numerical PDEs. But somehow, well, especially for high dimension, but my experience or what I know, my group with my students is that there are lots of practical theoretical issues. Practically, it's just very difficult to solve that optimization problems. And if you get most of the paper in the literature, you get a 10 to the -3 accuracy or something like that. But you cannot go down. You can go down further. So anyway, this talk, again, if anybody in the audience would know better in this topic, I would be grateful to know the literature. But in this talk, we try to provide the answer to this question somehow. One of the key issue here is the model space. Is this K1D, is the stable neural network space? Then you can do the analysis, you can also train it somehow, and then you can prove some theorem, you can numerically also looks good. And so, but these are some papers which you can find from archive, and some of them published. And I'll stop here. Thank you very much.
Great. Well, thanks very much. Looks like we have a few minutes for questions. If you go to the bottom of your screen, there's reactions. You can raise